Hello everybody. In this video we're gonna talk about the last part of or last method of evaluating the mass transfer coefficient. And as I mentioned before, we are not gonna go through the last part, which is the analogy. I think you can understand it easily if you check it in the textbook. It's just doing what we have been discussing before, that there are similarities between fluid mechanics, heat, and mass transfer, and it's trying to get relations from these similarities. But for the sake of time limitations, we are not gonna go through this. So the last method is about approximate boundary layer analysis, and this is similar to the previous method, which is the exact laminar boundary layer analysis, but we will notice there are two main differences here. The first is that this is approximate and this is exact, and by approximate we mean that there are some assumptions that we make, so the solution is not 100% accurate. It's very close to the actual or the main or the true results, but it's based on some assumptions, and that's why we cannot consider this as exact analysis. It's an approximate analysis due to this assumptions. The second is that we have here in the previous method, it was laminar boundary layer analysis. And in this case, it's just boundary layer analysis, which means that it includes boundary layers which are laminar and turbulent as well. And this makes this method more general than the previous method. So we're not going to go through the mathematical details of this method, but what we need to know about it is the main concept or the main idea or the basis of the calculations. So if you remember, in the exact analysis that we did before, we started with the fluid mechanics equations or the heat or mass transfer equations that describe the boundary layer, which were based on like theoretical equations or basic theoretical equations, like the continuity equation in mass transfer, like the equation of motion in fluid mechanics. And that's why we started with this equation and did all the derivations and the integration until we were able to get the final form of the mass transfer coefficient or Sherwood number. But in this case, it's based on another method of analysis, which is the mass balance analysis. So what we do in this method is that we take a differential volume of the boundary layer. We do mass balance on this differential volume with the thickness or width delta x, and we see how much mass or the rate of the species A going into this control volume, and the rate of species A going out of the control volume from up and down and right and left. And then we do the balance equations, we use the boundary conditions, and then we do the integration. So this is the main basis of this method. The integration includes some assumptions which make this method an approximate method. But just to make a long story short, this is the basis of this method. After doing the integration and after solving the equations, you will end up with these equations here. So we have this equation, which is very, very, very similar to the equation we got from the exact laminar boundary layer analysis for the local mass transfer coefficient. In the other case, it was 332. Here it's 323. So it's almost very, very close. And for the average, it's almost the same, or it's the same actually. And here you get these two equations, which represent the boundary layer or mass transfer in case, or mass transfer coefficient in case of boundary layer which is turbulent, which means the Reynolds number is greater than 3 million. And you have this equation here and this equation here for the local and for the overall mass transfer coefficients. We also have this case, which is the transitional, which is actually got from these two equations. So the way we get this equation is by integrating the local equation, or getting the average by integrating k dx divided by dx, or the integration of dx. So this is how we got this equation, this is how we got this equation. And in case of having a transitional flow, which is not turbulent and not fully laminar, we can do the same, and the derivation of this equation is also available in the textbook, so you can find it. But this is a combination of the laminar part and Reynolds part and the turbulent equation, and you see here there is the Reynolds T and there is the Reynolds L. The Reynolds T is the Reynolds calculated based on the turbulent or using the turbulent equation, which is calculated using this equation or this equation. And then we'll have this Reynolds L, which is for the laminar equation, which is this, and the Reynolds L is going to be the 2 million in this case, 200,000, I'm sorry. But anyways, you can use these three equations to describe the average mass transfer coefficient, and if you plot them, you would see that this is how the Sherwood number changes with Reynolds number. So I have this for different Schmidt numbers. So you see, as the Schmidt number increases, the Sherwood number increases, which is very, very logical. This is the dependence of Schmidt number or Sherwood number on Schmidt number. It's directly proportional to Schmidt power 1/3. So this is the relation. We see this increase, and you see that after 200,000 it starts to be transitional and the slope starts to increase. And here you have in the turbulent region the slope is much larger than here, which means that mass transfer coefficient as a value increases because the Sherwood number here is larger than here, and the rate of increase of mass transfer coefficient is higher. There is also one other observation that we can get from here, either from these two equations or from these two equations, which is the effect of turbulence on mass transfer coefficient. We saw it in the plot, but you can see it here as well. Here it's Reynolds number power half, while here it's 0.4 power 4/5, which is 0.8. So I have here 0.5 and here is 0.8, which means that, and keep in mind that in this case Reynolds number is much larger than the Reynolds number here. The maximum value of Reynolds number here is 200,000. The minimum value of Reynolds number here is 3 million. So this will have larger impact on or larger value than it is here, which makes sense, and this agrees with what we said in the very beginning, that the turbulence in the system has a great impact on the mass transfer coefficient, and that you increase the mass transfer coefficient by increasing the turbulence. So this is what we see from these equations, that the turbulent flow will have much higher mass transfer coefficient than the laminar flow. And this is what we see here. So just to wrap up this chapter and have everything together in one place, or the main points that we want or we covered in this chapter, the convection mass transfer coefficient is this equation. This is the flux equals mass transfer coefficient multiplied by the driving force, and in this case we use dimensionless parameters: Nusselt number, which is the convective force or convection mass transfer, divided by the diffusion mass transfer, or the ratio between them; Reynolds number, Schmidt number, the momentum diffusivity, divided by the mass diffusivity; Grashof number, which is the buoyance force, divided by the viscous forces. So these are the four mass transfer coefficients, and the four dimensionless groups, and we have these relations between Nusselt number, Reynolds, and Schmidt number for forced convection, between Nusselt number, Grashof number, and Schmidt number for natural convection. And we cover two methods of analysis: the exact laminar boundary layer analysis and the approximate boundary layer analysis. These are the equations in case of the local mass transfer coefficient. We have this equation for the exact analysis, and these are for the approximate analysis. And this is these are the equations that we have for the average mass transfer coefficients, which we actually use in most of the cases. And we have it here for laminar, we have it here for laminar, transitional, and turbulent flows. So this is all what we will cover in this chapter. We will talk more about the correlations that we can use to calculate the mass transfer coefficient in chapter 28, which is the after next chapter. And we will talk in more details about the shapes and the correlations for different degrees of turbulence and different geometries. So there will be more discussion about this. So we'll end this chapter here, and I'll see you in the next chapter, inshallah. Goodbye.